So this is my lab report for lab number 5, and I chose to do the human rocket computational experiment. So to introduce this lab, about 10 years ago, Felix Baumgartner partnered with Red Bull, and he jumped out of a balloon from an altitude of about 120,000 feet. For our purposes, is a little over 36,000 meters for physics principles. And I did this lab project with only GlowScript in computation because Felix Baumgartner himself did the experiment, and I'm making a model to try and make the best fit data for what he did. Over here on the right, I have the 3 physics principles I used. The first one is the drag equation in the y direction, which is the negative b, where b is a proportionality constant, times the magnitude of velocity squared times the direction of velocity. Since he's traveling down, this expression ends up being positive. Next, the force of gravity, which not much to explain here. We use this all the time. It's just negative mg in the y direction. And then finally, I have the momentum principle, Newton's second law, which can be derived into the velocity and position update formulas that I used for the while loops in GlowScript. And then right here is just kind of a preview of the little picture my GlowScript drew at the end, where yellow is where he started, blue is Felix, and then green is the path he took to get from there to there. So here's my initial conditions for the code. So I had the ball mass, the ball is just Felix, as his weight added to the equipment weight, which I estimated to be about 100 kilograms. Right here, we talked about he started from an initial position of 36,576 meters in the air. And then the most important part is this proportionality constant that I found through trial and error. So using sources on the internet, I found that he deployed his parachute at around 6,000 feet above Earth's surface, which for our purposes is a little over 1,800 meters. So I continued manipulating this proportionality constant until I got, this is a screenshot of a graph of my results. So he deployed it at 4 minutes and 20 seconds, otherwise known as 260 seconds. And I try to get this where he deployed it as close to 1,829 meters as I could. And I found that this is a fairly good approximation for B. I have 2 while loops in this code. The first one is pretty self-explanatory. I took it from our lab 2, where we did the drag equation and gravity and made that F net. That's pretty simple. I had T less than 260 because he deployed his parachute at 260 seconds. Next, I have, while T is less than 542, this is after this loop right here, because that's when he actually hit the ground at 542 seconds after he dropped. And you may be asking why I have the velocity equal to this negative 6.5 and the net force equal to 0. I did some calculations and found the average velocity using the displacement and using the change in time from when he actually hit the ground and when he deployed his parachute. And assuming F net is 0, meaning that he's going to travel at that constant velocity all the way to the ground so that he arrives safely on his feet. Here's a visual demonstration of what happens when I run the code, where right here is that little diagram of what Felix would look like. And yeah, so here's 2 screenshots of my graphs. So right here's the position. So right here at 260 seconds is where he declined at a consistent, not as steep of a slope, and then fell to 0. And right here is the velocity, which is interesting. So he peaks at around negative 140 meters per second. Right here, he deploys the parachute and immediately slows down all the way until he hits the ground. However, in the actual jump, it was found that his top speed, I was off by a bit, was 382 meters per second before he deploys the parachute. So obviously, there's some sources of error in my computation. One of these could have been incorrectly estimated B value. Another one could have been there's other forces on the system besides gravity and drag that I didn't account for. There could also be drag in the X direction as well. And then finally, incorrect measurements. So his weight, him in the backpack, may have not been 100 kilograms exactly. And also the distance I found online could be a little off. There's a lot of variation in that distance. I try to make it as uniform as possible. So we weren't given what if and what does it mean questions for this lab, but I improvised and pulled 2 suggestions they had in the human rocket experiment. So for the speed of sound is 343 meters per second. He did surpass this in the experiment, but like I said, my model did not predict the speed due to some sources of error. And then an appropriate model for air resistance, we talked about this in the introduction, it's the drag equation. That's before deploying the parachute though. After, I think it's appropriate to say that F net is 0, because if you set the drag equal to the gravity force, that means that he will land safely on his feet when he's at that consistent or that constant velocity.